In this question, he has given a generating station has 3-section bus bars which is connected to a tie bar of 6% reactor. Okay. Now this tie bar reactor is rated at 2500 kVA, or you can simply say it as 2.5 MVA each. Okay. And each generator, you have 3 generators here. Each generator is of 2500 kVA with 12% reactance, that is double than that of tie bar reactance. Okay, which is connected to one section of the bus bar as shown in figure. Now we have to find the short circuit input, that is what is the steady input to a dead short circuit between the lines. That is the important point here, between the lines on section 3 of the bus bar without connecting the reactor. Okay, and with connecting the reactors. Okay, now let us analyze first one without connecting the reactors. Now without connecting reactors, that means you don't have any tie bar reactors, we have only generator reactors, that is 12%. Okay, now this is 12% given for each generator. Let us take this as generator 1, which is connected parallel to generator 2. Okay, this is of 12%, and we have generator 3 is also 12%. Now fault takes place at section 3. Since we don't have any reactors here, it can be here or here also. Okay, but it is on section 3. Now what is the fault impedance up to fault point, or you can say it as what is total percentage of reactance up to fault point. These three are connected in parallel, which is equal to 12 parallel to 12 parallel to 2, that is 12 parallel connected. Three values are same here. Okay, 12 by 3, which is equal to 4%. Now what is the short circuit input? Short circuit input is equal to 2500 into 100 by 4. So 4%, 4 by 100. Okay, 2500 into 100 by 4. Remember, this is rated in kVA. Okay, now this is equal to 62.5 MVA. So option D is correct for the first question. Now when tie bar reactances are connected to the bus bar, okay, now what is the equivalent diagram here when reactances are connected? This is 12% generator reactance, 6% tie bar reactance. Similarly, this is 12% generator reactor, 6% tie bar reactor for section 1 and 2. And now for 3, okay, this is 12% generator reactance and 6% tie bar reactance. The fault takes place between the two points of the generator and tie bar reactor. You can see here the fault takes place in figure. The fault takes place in between generator and reactor. So fault takes place between these 2 points. This is fault point F. Now what is percentage of reactance up to fault point? It is given as 18 parallel to 18 plus 6%. Okay, that is 2 are connected in series in parallel with 12%, or you can write this as 9 plus 6% in parallel with 12%, which is equal to 6.67%. Now what is short circuit input? Now short circuit input is equal to kVA rating by percentage of reactance. This is 6.67 into 100. You will get it as 37.48 MVA. 37.48 MVA, that is option A.
Consider the following oscillator circuit shown in the ideal op-amp. Determine the frequency of oscillation. See, from the circuit shown in the question, we came to know that this is a Wien bridge oscillator using an op-amp. So for Wien bridge oscillator using an op-amp, the frequency of oscillation is given by 2 pi R1 C1 R2 C2, whereas this is R1 C1 C2 R2. If we substitute the given respective values, we will get F0 as a 472 kilohertz. Hence option B is correct. Here in the above circuit, the value of R1 needed to maintain the oscillation. See, the condition for oscillation is, suppose if we assume this resistance is R2, this resistance is R1, R2 must be 2R1. That is, here R2 is 10k, 2R1 means R1 is 5k. Hence option B is correct.